Hi, welcome back. In this lecture, I would like to introduce the usage of MEEP for modeling waveguides. This is a very simple example, and we're going to go through this example step by step. To start with, what is a waveguide? Well, a waveguide is a structure that guides waves, for instance, electromagnetic waves, with the goal of having minimal loss of energy. And the waveguide achieves this goal by restricting the transmission of energy to one direction. So in these slides, for instance, we have an example of a waveguide that is our material characterized by permeability and the electric constants mu and epsilon. And the waveguide is restricting the transmission of a wave along this direction. Without having a waveguide and the physical constraints of a waveguide, what will happen is that the wave intensity will decrease according to the inverse square law as they expand in three-dimensional space. So we'll expand like this, and our waveguide is constrained to move along this direction. So when it comes to the MEEP simulation code, Jupyter Notebook, Python Notebook to simulate this waveguide is available at this link. So let's see the problem we want to solve, the straight waveguide. For our first example, we want to examine the field patterns that is excited by a local source in a waveguide. So what we're going to do is to put a source here using MEEP and then to see how this electromagnetic wave is going to propagate within the waveguide. Our waveguide is characterized by a medium that has an epsilon, that is the electric constant, that is a frequency independent, so it won't depend on the frequency of the wave. And we set epsilon to 12 of this material, and also we will set the width, so this height here of the waveguide equal to 1 micrometer. If we go back to the previous lecture on the units in MEEP, our unit length in this case will be A, and is going to be 1 micrometer. Whenever we have a Python code, the first thing is to load the MEEP module so that we are going to have access to all the functions that are provided by the MEEP code. Together with the MEEP function, we also need to load some functions that are needed for the visualization or for the post-processing. In particular, we also loaded the matplotlib library and the pyplot that will allow us to make nice plots. The first step in designing simulation in MEEP is to define the simulation domain. We're going to put a source at the end, at one of the end, and watch the field propagates down the waveguide in the x direction. So in this case, what we're going to do next is to put a source here, and then we will look at the wave propagating in the x direction. We will use a simulation domain that is defined by this call. So we call the mp.vector. So what we called vectory in the previous lecture in the Python interface is called vector3. So the cell is going to define all our simulation domain, and we will need to provide the site. So in the x direction, we're going to have 16 micrometer, and then we're going to have 8 micrometer in the y direction. And since we are doing only two-dimensional simulation, we're going to set to 0 the size in the z direction. After we defined our simulation domain, so that's the whole box that we want to define, it's time to define the geometry and the material of the waveguide. So to add the waveguide into the simulation domain, we are going to use the geometry object. So we define a geometry object as following. We tell first we say what is the shape, the geometry, by using mpe.block. In this case, we say that the waveguide has a parallelepiped square, so just a rectangle. In the rectangle, we need to provide the size. So we have the size is our A. In the y direction, this is equal to 1. And then we want to define that in the x direction and the z direction, the size is as long as the simulation domain. So we're going to use infinite and infinite. So just just a shortcut to say that it needs to cover all the domain. Also, we want to tell where is center, so we define the center in 0, 0, 0, that is here. And also we want to tell what is the property of the medium. So in this case, we want to set the medium properties. We want to set to epsilon equal to 12. So by default, epsilon is 1 in here and here, and we are going to set this special material to have epsilon equal to 12. So just to summarize, the waveguide is specified by a block with the epsilon equal to 12, center at 0, 0, which is at the center of the cell. By default, any place where there are no objects, there is R, so there is epsilon equal to 1, and in our waveguide, epsilon is going to be equal to. The next step that we want to add is to add to the domain a source. So we have a structure and need to specify the current source using the source object. The simplest thing is to add a single point source GZ, and we're going to use a source object that is mp.source object. We define it as a continuous source in a MEEP, and we provide the frequency equal to 0.15. So we give the source a frequency of 0.15 and specify the continuous source, which is just a fixed frequency sinusoidal source that has the expression exponential minus I omega t. And when this source is turned on, well, we could specify it. If we don't specify anything, by default, the source starts at t equal to 0. So our start at the beginning of the simulation. We also specify what is the location of our source using center mp.vector3, and then we provide the location. So it's going to be -7. So remember that the 0, 0 is here, and then this is 16, and so this is going to be the position of our source in the x direction, and then it's going to be 0 in the y direction here. Typically, we'll just leave a little bit of space here between the boundary and the source, just to avoid any problems with the boundary condition. So we don't want to have a source exactly on the boundary. Sometimes it gives some numerical problem. I discussed a little bit about the MEEPs units in the previous lecture. In the MEEP units, frequency is specified in units of 2 pi multiplied by c, which is equivalent to the inversum of the vacuum wavelength. So if we do the translation to the MEEP units, 0.15 corresponds to a vacuum wavelength of about 1 over 0.15, that in dimensional units is equal to 6 to 6.67 micrometer. So this is a wavelength of about 2 micrometer in the epsilon equal to 12 material. So in the waveguide, the wavelength is about 2 micrometer. This is nothing else than also saying that the waveguide is half of the wavelength wide. So by construction, we design a waveguide whose size is half of a wavelength wide. So that's very important for the waveguide. It's now time to define the boundary condition. In particular, we're going to use absorbing boundary condition, so A, B, C, or in particular, we're going to use the PML technique. Absorbing boundary in MEEP are defined by using a PML, and what we're going to do is we're going to add a fictitious absorbing material. So we're going to add a material at the boundary that is our PML. To add an absorbing layer of thickness of 1 micrometer, so this thickness is going to be 1 micrometer, is as simple as that. We defined our PML layers as following, so as mp.pml, and then the size, that is in this case 1 micrometer. An important point to take in account when designing simulation for MEEP is that the PML layer is inside the cell that is our simulation domain. In this case, our PML overlaps with our waveguide. So we'll probably absorb waveguide modes exiting the boundary. So let's talk a little bit about discretization in space and in time. MEEP deals with resolution in time and space by introducing the resolution. So MEEP will discretize the resolution variable that gives the number of pixels per distance of units. Right? So remember that our dimensional units in the space is normalized over one micrometer. So we will set, so for instance, if we have a resolution equal to 10, we will set the resolution to 10 pixel per micrometer, that is our A. This corresponds to around 67 pixels per wavelength, or around 20 pixels per wavelength in the high index material on our medium that is defined in the waveguide. In general, as a rule of thumb, at least 8 pixels per wavelength are needed in the highest dielectric, in this case our waveguide. So this resolution is going to give a discretization in space of 160 by 80 cells. So we are almost there, so we are ready to run the simulation. The last step is to define the simulation object. So the simulation object is based on all the previous defined object and is defined as follows. So we define a sim as mp.simulation. We provide the simulation domain. We provide the boundary condition as PML layers. We provide where is our waveguide, where is our source and this frequency, and then finally the resolution in space. After the simulation object has been set, has been constructed, we can finally run the simulation. So the time step of the fields we can run until a time of 200 by basically set it up until equal to 200 as an argument to the sim.run method. So at this point we have the simulation, and what we can do is just plot the final results. So we start a figure with this kind of definition, and then we decide to plot fields mp.z, and then we're going to do the plot show in order to visualize. And this is going to show us the easy components of the fields that superimpose on the previous domain plot. So in this case, this is the all cells, what MEEP calls cells. And then we have the boundary condition that is 1 micrometer, and then we have the source of our current here. And this is basically at a time to 200 the easy component. You see that is propagating along the z direction. This is the last slide. Talk to you soon.